And this was a very good intro for what follows. So we said, so we're going to talk about residuals. Okay. So residuals and all the variation plus variability. Explained or not explained by the regression line. Explained or not by the regression line. That was a very good question that you had. Okay, so let's go back to the regression line. So let's suppose we found this is the regression line, and this is y hat equals b1x plus b0. This is the slope, and this is the y-intercept. As I mentioned a minute ago, it has to pass through anywhere, doesn't matter where, I don't know where, I'm just going to say this, it has to pass through that point, which is the mean of all x values in the data set or entries, and the y hat. So this point is the point x bar comma y bar. X bar being the mean of the x values, and the y bar meaning, so this is again x, but it's basically called explanatory. And here is y, but it's basically called response variable. And we have the cloud here. I'm not gonna graph all the cloud or plot it, the scatter plot, but I want to plot one. So I'm going to draw a horizontal line through this point, which is the y hat. I'm going to draw a vertical line through this point, which is x bar. Okay, so let's say this point here, give me any x value. I don't care what you give me, and give me a y value, because it will be easier for me to explain what happens here.
X can be 10.
Good. And y?
Y can be 8.
You said 8.
8.
Yes?
Yes.
Perfect. So this point here is 10, 8. 10, 8. So it's an actual value. Okay? The corresponding to 10, to x equals 10, remember, was that predicted. So this height here is the y hat for x equals 10. This is the y value, this height is the y value for x equals 10, which you gave me 8. So obviously this is below 8, so let's give it a number.
6.
6. So this height is 6. This y minus y hat is what we call the residual. So the residual is y minus y hat. We calculated it a few minutes ago. So in our case, y is 8 minus 6. So the residual is 2. Can the residual be negative? Yes. I'm not gonna put this on the graph because I picked a positive residual, but I can have this observed value right here, and then the residual will still be y minus y hat, but it will be a negative number, so it will be below the expected. This is the above the expected, so that's why it gave us a positive number. Okay. The next thing that I would like to talk about is what is this distance between this point and this point. So notice that this goes through y bar, right? So this is basically y minus y bar. So this is y minus y bar. This is called total variation. Total from the observed to the mean of the y. This is the total variation. So this is y minus y bar. Okay, this is the last piece that I want to talk about. What is this piece? Is y hat minus y bar. Y hat minus y bar. This piece is the variation explained, the variation in the response variable, explained by the regression line. So y bar, y bar minus y hat is the explained variation in y, which is the response variable, explained by what? By the regression line. So now, because these can be positive and negative, this can be positive and negative, this can be positive, we just had a negative, I just gave an example with positive, but all these can be positive or negative depending on where they are. We are going to look at the sum of the squares. So the sum of the squares for the total, which one is the total? This one.
I have a question.
Yes, I'm ready.
Just want to make sure I'm tracking.
Yes, yes.
The variation explained by the regression line, the equation, that's the mean versus minus the y hat, right?
Yes, it's
Okay.
it's
Y bar, right?
oh, you're right. I should have written it as y hat minus y. In this case, in my drawing, yes. Thank you. You're right. Because in my example, I could have been here, right? But in my example, you're right. Is y hat minus y bar. We're gonna square them, and it doesn't matter.
Okay.
But I want to keep it as it is in my drawing. Thank you. Thank you very much. We're going to square them so the sign will not matter. Yes, thank you very much. So the total is y minus y bar. The explained is y hat minus y bar. The unexplained, or the residual, we call it, is y minus y bar. Y minus y bar. Okay. Thank you so much. Was it Gabe? Thank you.
Yep, that was me.
Okay, total. The total is y minus y bar. Remember, even if I make a mistake, well, I don't want to make a mistake, but even if I make a mistake and write it 1 minus 2 or 2 minus 1, it will be squared. So the sign will go away. Okay, so this is the explained plus the unexplained. Okay, so the explained, of course, they have to have a sum, and of course they have to have squared. Absolutely. The explained is y hat minus y bar. Y hat minus y bar. The unexplained, y minus y bar hat. Okay? Any questions on this?
No.
Okay, so now the only thing I was going to mention before we look at some problems is, so that's my page 3, okay, is how we get the coefficient of determination. So again, two different things here. Coefficient of correlation, and we know for population, raw, for sample, lowercase r. Now, coefficient of determination for population is r squared. For sample is r squared. You can say, what's the connection here? Well, the coefficient of correlation shows what type of relationship we have between two variables. strong positive, positive, no correlation coefficient, 0. Negative, strong negative. That's what the coefficient of correlation is telling us. But what about this? And I will put a note, first of all. For linear regression, only for linear regression, coefficient of determination is r squared. This r squared equals coefficient of correlation squared. It will not be determined, the coefficient of determination will not be determined by squaring the correlation coefficient for other models. Okay, finally, what is it? That's the most important part. So r squared gives the proportion of total variation in response variable explained by the linear regression line. Of course, the least squares. I want to put it in. Least squares. By the least squares regression line. So this is totally different than the coefficient of correlation, but it can be determined by squaring r. So here's an example before we continue. Let's say I get that r squared is 0.32 for a particular data set. What does this mean? It means that the proportion of 32%, so r squared is 32%, is the proportion of total variation in the response variable explained by the least squares linear regression line. So the rest of 68% is unexplained by the linear regression line. It's explained by something else. So this is not a fantastic answer. It's not as good as we wanted it to be. But if r squared is, let's say, 0.98, then I will say 98% is explained and 2% is unexplained. So this is a good model because it explains 98%. I can draw good conclusions, reliable conclusions. But from here, not that much, because 68% is unexplained. I don't know where it's coming from or what the situation is. Any questions so far?
No, thank you.
Okay, one other thing that is important here, and we'll start problems. Is a condition. There is a condition for these residuals. So let's suppose I plot the residuals. So this is the residuals, right? And this is the explanatory variable, or x. And let's suppose I get something like this. So that's called the residuals plot. This means that there is a constant error in the variance. Which means the linear regression is appropriate. the linear regression. So why we would want to plot the residuals versus the explanatory variable? To see if there is a pattern. If there is no pattern, it means that the constant error in the variance is, so it's a constant error. All observations have a constant error. So that means that the linear regression is appropriate as a model. But what if I plot the residual plot and I get something like this? So these are the residuals. Residuals versus the explanatory variable. Linear model is not appropriate. Linear model, linear regression model, not appropriate. Because there is a pattern in the residuals. We don't want any pattern in the residuals. If there is no pattern, it means that the constant error condition is fulfilled, and then the linear model is appropriate. But if I see any pattern in the residuals, I'll say, oops, this is not a good model for the data that I have. It may be good for something else, but not for this. The spread of the residuals has to be the same for all values of the explanatory variable. Here, they're not the same. For lower values are higher, for middle values are lower, for higher values again are higher. There is a pattern. There is a pattern. The linear regression model is not appropriate. That's why we look at the residual plot. That's pretty much all in chapter 4 that